Welcome to today's webinar. The topic today is bucket foundations with geotechnical design checks in RFEM 6. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the webinars, technical content of the website, customer projects, and so on. I will be the moderator today and I will answer your questions during the webinar. My colleague Ann-Kathrin Danwert will do the presentation. She works in the development team for concrete, and she's also member of the customer support team. At first, I say something how you can ask questions. Just press the button with the question mark, then enter your question in that field, press send, and I will receive your question and then I will answer you. The other way is to watch the entire webinar and email to info@dlubal.com. Then, that's for the moment all from my side. I hand over to Ann-Kathrin. Ann-Kathrin, it's your turn.
Hello and welcome from my side as well. My name is Ann-Kathrin Danwert. I work as a product and solution engineer at Dlubal Software, where I'm deeply involved in the modeling and design of concrete foundations, along with geotechnical design checks in RFEM 6. Before we switch to the program, I would like to give you a brief overview of today's webinar agenda. We will start by taking a look at the model and the base data, so that you can get an overview of the prepared example. After that, I will show you the different foundation types, such as foundation plates, block foundations, bucket foundations, and step foundations. In the next step, we will focus on the bucket foundation and go through it in detail using the example model. Afterwards, we will take a look at the additional foundation loads. This includes surface, line, and concentrated loads that can be freely defined on the isolated foundation. In addition, we will take a look at earth covering and groundwater, which are automatically taken from the soil definition and only need to be assigned to the corresponding load cases. Building on this, we will deal with the corresponding load combinations, action types, and design situations. I will show you the automatic and manual generation of characteristic load combinations, the definition of actions, as well as the required design situations in the ultimate limit state and the serviceability limit state. After that, we will move on to the reinforcement input. Here we will look at both reinforcement meshes and bars within the foundation design. Another focus will be on multi-layered soils with bore profiles. I will show you the soil definition, followed by an overview of the geotechnical design checks themselves. I will present the design checks based on the graphical results and ratios, including overall stability, bearing resistance, sliding resistance, as well as the case of loads with large eccentricities. After that, we will take a look at the printout report. There we will look at the foundation properties, the governing design checks, as well as the reinforcement representation. Finally, I will show you the modeling of multi-layered soils using soil solids from the Geotechnical Analysis add-on. Let us now switch to the program. I have already prepared a reinforced concrete building with concrete columns for you. First, I would like to show you the base data of the model. In the base data, you can define, along with other settings, the model name, the project information, the model type, the building grip, as well as the activated main objects. In this webinar, we are working with a 3D model. Accordingly, members, surfaces, and solids are active. However, the soils will only be required in the final part of the webinar when we model the soil solid. Let's move on to add-ons. For the modeling and designing of foundations, the Concrete Foundations add-on must be activated. In addition, I activate the Geotechnical Analysis add-on as a soil solid will be created at the end. Let's go to Standards 1. In this dialog, the standard groups and national annexes used for the design can be defined. Here I'm working accordingly to the Eurocode, so no changes are required in this case. By activating the Concrete Foundations and Geotechnical Analysis add-ons, Concrete Design, along with Geotechnical Analysis, is now available within the design standard groups. In addition, you can find further standard groups and special design modules here. For example, for tower, piping, and craneway design, as well as steel and timber joints design. In the section Settings and Options, you can find, along with other settings, options for global and local access, as well as the various tolerances. I will leave the representatives out of this webinar. In the model parameters, you can define the product location. This information is used by the load wizard, for example, for snow, wind, and seismic loads. The location can be selected directly on the map. Here I select our main location in Tiefenbach. The integrated GeoZone tool already provides the required factors for the load wizard. By activating the Concrete Foundations add-on, an additional folder is shown in the navigator. Under Single Foundations, you can find all foundations defined in the model. They can be edited or created via right-click. Below that, the design situations are listed. These are used later for the evaluation of the geotechnical design checks. In Objects to Design, you can define which foundations are actually designed. Using Objects to Exclude, foundations can be excluded from the design if required. You can also find the geotechnical design configurations and concrete design configurations, which allow you to control the design settings of the entire project. In addition, the Concrete Foundations add-on also adds the reinforcement folder. Here, the concrete durability settings, meaning the exposure classes, can be defined and used for the foundation design. The concrete durability settings can be defined very easily here. In the central input area, you define the governing exposure classes separately for reinforcement and concrete. On the right-hand side, the settings are displayed graphically. Since multiple exposure classes can be saved, different exposure classes can be assigned to specific components or foundations. The selected settings are then used directly from the concrete cover and foundation design. By activating the Concrete Foundations add-on, the Geotechnical Analysis folder is also shown in the navigator. The borehole profiles are available here, as they are required for defining multi-layered soil in the foundation area and can also be used without the Geotechnical Analysis add-on. Single-layer soils can be defined directly without borehole profiles. The entries, pyroresistance, and soil solids are only available when the geotechnical add-on is additionally activated. In the context of foundations, they are only required if the foundations are designed using a soil solid. Under loads, within the load cases, you will find the additional foundation loads, which is edited by the Concrete Foundations add-on. Here, the previous mentioned surface, line, and concentrated loads can be defined acting directly on the foundation. In this area, you can also see earth covering and groundwater. These loads are taken automatically from the soil properties. I will explain the soil definition in more details later in the webinar. Before continuing with the foundation types, I will briefly complete the model by showing you the base objects. Under materials, the relevant materials are already defined. The C3037 concrete, the reinforcing steel, and the soil materials required for later for the foundation. Materials shown in blue in the navigator are currently not used in the model, but are already available for later assignments. In this context, I will show you the material library and how new materials can be created or existing ones modified. RFEM 6 provides a material library which can be accessed directly when defining materials. The materials are organized by categories, such as concrete, steel, or for example, soil, and can also be found using the search function. This makes it easy to find the required materials quickly. For the materials, the relevant material properties are already stored, for example, for concrete and foundation steel according to the applied standards. For soil materials, the material properties are usually used as a starting point. The soil properties then need to be adjusted to the specific project, for example, based on a geotechnical report. In this way, materials can be selected easily while you still keep full control over the project-specific material parameters. Under cross-sections, the cross-sections of the members are defined. For example, here, the column cross-section used in this model. The thicknesses are assigned in surfaces, each in combination with the corresponding material. Below that, you can see the base model objects, such as nodes, lines, members, and surfaces, as well as the openings including in the model. In the lower part, you will find the types for nodes, lines, members, and surfaces, for example, supports or hinges, which are used to define the structural behavior of the model. With this, the essential model settings are defined, and we can now move on to the next step, the foundation types. From this point on, the foundation modeling becomes relevant. In RFEM 6, foundations are assigned to supports. For this, I open a nodal support in the Types of Foundation folder. Here I have already prepared a support and assigned it to 3 nodes for which I want to define identical foundations. Under Options, I will now activate Foundations. This adds an additional Foundations tab where new single foundations can be created or existing ones selected. In the Edit Single Foundation Basic dialog, the different foundation types are available. These include foundation plates, with or without reinforcement, block foundations and bucket foundations with smooth or rough bucket sides, as well as step foundations, which are currently still under development. However, the geometry can already be defined. In this dialog, the materials for the foundation plate can also be selected or created. The design properties are activated by default, but can also be switched off or on if required. When the foundation type is changed, the image on the right-hand side of the dialog is updated accordingly. In the Geometry tab, the governing dimensions of the bucket foundations are defined. The dialog is divided into several sections. First, the dimensions of the foundation plates are defined. Here you can specify the plate dimensions in the X and Y direction, as well as the plate thickness. I increased the plate dimensions to 2.5 meters by 2.5 meters, while keeping the plate thickness unchanged. Below that, you can find the bucket section. Here, the bucket height and the embrace depth of the column are defined. In addition, the bucket dimensions can be defined separately for the X and Y direction. For each direction, you can specify the bucket wall thickness and the column clearance. For this, the inner wall inclination of the bucket is determined, which you can see here. This allows both vertical and inclined buckets' inner walls to be modeled realistically. In the eccentricity section, an eccentricity position of the column can be defined, again separated for the X and Y direction. In the lower part, the column geometry itself is defined. In addition, a base plate at the column base can be activated. This information is passed to the steel joints add-on and can be used for further modeling and design. After defining the geometry, we move on to the reinforcement settings. These are divided into several tabs to keep the input clear, structured. First, we will see the general reinforcement settings. Here you define the reinforcement material and select the reinforcement type. For the foundation plate, for example, reinforcement meshes, rebars, or a combination of both can be used. For the bucket, the stirrup reinforcement is defined separately. Here you can choose between horizontal stirrups enclosing the column or stirrups located entirely within the bucket wall. These settings form the basis for the detailed reinforcement input in the following tabs. Next, we switch to the concrete cover tab. Here, the concrete durability is assigned to the individual area of the foundation. For example, the top and bottom of the reinforcement plate, the plate sides, and the bucket itself. Based on the selected exposure classes, the program determines the concrete cover accordingly to the standard separate for each area. Alternatively, the concrete cover can also be defined manually without considering the assigned concrete durabilities. Next, we define the reinforcement of the foundation plate. The reinforcement layers can be defined separately for top and bottom. For each layer, you can define the reinforcement directions in X and Y, the reinforcement areas, bar diameters, and spacing, as well as an optional anchorage. By dividing the plate into distribution areas, the reinforcement can be adapted to the actual internal forces. In the final step, the reinforcement of the bucket is defined. Here, a distribution is made between horizontal and vertical stirrups. For both reinforcement types, you can define the bar diameters, the number of stirrups, or alternatively the spacing, as well as the distribution over different areas of the bucket. In the Soil Properties tab, we can define the subsoil for the foundation. First, the soil conditions can be specified. They can be sent to consolidated or unconsolidated and influence the geotechnical design checks. Below that, you select the soil definition type. Here, a single layered soil is available. In this case, the soil layers, the groundwater level, and the earth covering are defined entirely within this dialog. If we work with multi-layered soils, either using boreholes or soil solids, the soil layers, groundwater level, and earth covering are completely defined corresponding to the borehole profile or the soil solid. In addition, the soil parameters can be defined in this tab. These mainly include the friction angles for the base friction and wall friction. On the right-hand side, you can see a graphical representation of the soil layering, which allows you to check the defined layers. In the next section, you can find the geotechnical design configurations. Here, all relevant partial safety factors for the geotechnical design checks are stored centrally. You can, for example, activate or deactivate design loads, define settings for bearing resistance, sliding resistance, and other geotechnical design checks. Adjust the partial safety factors individually, for example, according to a national annex or project-specific requirements. This section is important for foundations as it defines which design checks are performed and which safety concepts are applied. Finally, the concrete design configurations are available. They control the concrete design of the foundation and are structured independently of the geotechnical settings, while directly using the foundation geometry and reinforcement. Here you can, for example, define material parameters and partial safety factors for the concrete design, control the handling of minimum and maximum reinforcement, define settings for punching shear, define the location of design sections, as well as set the limit for the compression zone height. These configurations allow the concrete design to be carried out in compliance with the standards while still being adapted to project-specific requirements. Now we move on to the additional foundation loads. For this, I go to the Loads folder in the Navigator, open Load Case 1, and select Additional Foundation Loads. The following load types are available: surface loads, line loads, concentrated loads, as well as earth covering and groundwater. Starting with the surface loads. They can be applied directly to the entire foundation by selecting the corresponding foundation and define the load magnitude. The line loads work in a similar way. Here you can additionally define 2 points on the foundation between which the line load acts. The input is defined using ordinates which always refer to the foundation node. Now to the concentrated loads. Here as well, the load position is defined using ordinates relative to the foundation node, and the load components in the X, Y, and Z direction can be specified. The earth covering is generated automatically by the system. It is not defined directly here, but controlled via the soil properties when editing the foundation. The same applies to the groundwater, which is also generated automatically based on the soil definition. Let's move on to the load cases and load combinations. First, I go to the load case and open the self-weight load case. This load case is created and activated by default in RFEM 6. At this point, the self-weight is applied without soil solids, meaning only the self-weight of the load-bearing structure above the foundations. For the foundation design, it is important to additionally activate the self-weight of the concrete foundations. Once this option is activated, a second tab appears, which allows us to control the individual components separately. The self-weight of the foundation structure, the earth covering, and the groundwater. This separation is intentional as the individual components can have different effects. The groundwater, for example, can have an uplift effect and therefore act in a relieving way. For this reason, it is recommended in practice to define the groundwater in a separate load case. This ensures that the most unfavored static case is considered for the geotechnical design checks, for example, for uplift or sliding verifications. After taking a look at the self-weight load case, I will switch to the self-weight for soil solids load case, which is created by the Geotechnical Analysis add-on. In the self-weight for soil solids, the self-weight of the soil solids is activated by default. For a realistic foundation design, we need additional load cases, which we will then classify and combine correctly. I therefore create a separate load case for groundwater. For this load case, I use the action category GQ, permanent imposed. As mentioned before, groundwater can have a relieving effect on the foundation. By defining it in a separate load case, this effect can later be considered selectively in the load case combination or intentionally excluded in order to represent the most unfavored case. Next, I create a snow load case using the load wizard. I go to the load assistant folder in the data navigator and select snow loads. A new input dialog opens. First, I select the roof type. Here, flat or monopitch and dual pitch are available. I choose flat monopitch. Next, I define the roof corner nodes. The order is shown graphically on the right-hand side. I select the nodes clockwise, A, B, C, and D. Under Load Cases, I click Generate Load Cases. The entry is not longer highlighted in red and now is fully defined. Optionally, the shape coefficients and snow loads can already be reviewed here. In the last tab, you can find the tolerances, and I confirm with OK. The snow load case is created directly under Load Cases. I then rename it to Snow. With this, the snow load case is created. I have applied the snow loads only for the flat roof so far. However, on the first floor, there is an overhang, which is not captured automatically by the load wizard in this case. To include this area as well, I simply define a surface load manually. In this case, this is much faster. For this, I go to the corresponding snow load case, define a surface load, assign it to the overhang, and use the same load magnitude as for the remaining snow load. Before switching to the actions, I create an imposed load case. I apply an imposed load of 5 kN per square meter. For this, I go to the imposed load case, create a surface load, and assign it to the corresponding surfaces on the ground floor and the first floor. With this, the imposed load is included in the model, and we can now move on to the actions in the next step. After the load cases, we take a brief look at the actions. These are generated automatically by RFEM based on the defined load cases. In most cases, no changes are required here. The following actions are created from the load cases. Permanent from the self-weight of the structure, including the foundation, self-weight, and earth covering. Permanent soil for the self-weight of the soil. Permanent imposed for the groundwater load case. Snow ice loads for the snow load case, and imposed loads for the imposed load. Now we switch to the Design Situations tab. For this example, we only need Design Situation 1 and 2. The two additional design situations, frequent and quasi-permanent, are not required here and can therefore be deleted to keep the model clear. For the geotechnical design checks, we now create two additional design situations. First, a design situation of the type equilibrium. This is used for equilibrium checks, in particular for verifications such as overturning or uplift. Second, we create a design situation of the type accidental. This is required to represent accidental actions in the geotechnical design checks. With this, all relevant design situations are defined, and we can move on to the load combinations in the next step. For this, I open the Base tab and have a look if the combination wizard is activated. If the combination wizard is activated, the option automatically assign corresponding load combinations is active automatically as well. In this case, RFEM creates the load combinations and at the same time the corresponding combinations fully automatically. These can later be found in the Load Combinations tab as well as the assigned characteristic combinations. The assignment is essentially important for the geotechnical design checks, for example, for bearing and sliding resistance. These checks require characteristic load combinations and can only be performed if they are assigned correctly. Alternatively, a manual assignment is also possible. If the combination wizard is not used and the load combinations are created manually, the corresponding characteristic combinations can be added here via the drop-down menu. Once the load combinations and the corresponding combinations are defined correctly, we move on to the definition of the boreholes in the next step. First, I go to the Geotechnical Analysis folder in the Data Navigator and create a new borehole. This opens the Edit Borehole dialog, where the different input options are available. I start by defining the soil layers. For each layer, I select the corresponding soil material from the drop-down list and then define the layer thickness. First, I define the top soil layer, where I select gravel and set a layer thickness of 1.5 meters. Below that, I define the second soil layer. Here, I select clay with a thickness of 2 meters. The next layer is peat with a thickness of 1.2 meters. Below that, I define another clay layer, this time with a thickness of 3 meters 40. Finally, the bottom soil layer is defined as peat with a thickness of 2 meters 70. In this way, the subsoil is built up layer by layer from top to bottom. After defining all soil layers, I define the groundwater level to 0.5 meters. The groundwater level is specified using a z-ordinate and refers to the ground level. The borehole z-coordinate is set to minus 0.2 meters here. This information is important as it is later used for both groundwater loads and geotechnical design checks. With this, the borehole profile is fully defined. The defined soil layers and the groundwater level are now available for the foundation design and the geotechnical design checks, but still need to be assigned to the foundations. For this, I open the Edit Single Foundation dialog again and switch to the Soil Properties tab. Here I select the definition type multi-layered borehole, and RFEM directly detects the borehole profile we just created. The soil layering can be checked graphically on the right-hand side. After defining the loads, the load combinations, and the subsoil via the borehole profile, we can now start the calculation. Now I run the Concrete Foundations add-on. During the calculation, the geotechnical design checks as well as the concrete design of the foundations are performed automatically from the previous defined design situations. I start the calculation and then take a look at the results and the evaluations. I deliberately start in the static analysis because it allows for a very good plausibility check. It is important to note that the standard static analysis in RFEM initially only considers the model up to the supports. This means that in the global structural model, the foundations are not calculated as 3D solids. Instead, we obtain supports reactions at the nodes. For the foundation design, additional loads are considered, such as self-weight of the foundation, earth covering, or groundwater, depending on the active load case. The current evaluated load case is shown here. For this reason, I take a look at results, nodal, support forces with foundation loads in the static analysis. Here I can see the support forces from the structural analysis along with the applied foundation loads. These are the governing forces that are then used by the Concrete Foundations add-on for the further design. After the static analysis, this view is very useful to check whether the foundation loads are plausible. I am now in the Concrete Foundations drop-down menu and first see the different result views. In addition to the utilization at nodes, I could, for example, display the reinforcement of the foundation or directly the governing results. I start with the governing results as they provide a very good overall overview of all design checks. In the table, the results are shown separately by nodes. In my example, these are node 14, 17, and 19, which are exactly the 3 nodes to which Foundation 1 was assigned earlier. For each of these nodes, all performed design checks are listed. To improve clarity, I first hide the serviceability limit state and the ultimate limit state. This leaves only durability and concrete cover checks, checks for precast concrete elements at the bucket, and checks related to general reinforcement rules. Since these checks are not decisive for the current overview, I also switch off the level of detail. I now enable the ultimate limit state again. Here we see the typical governing design checks such as bearing resistance, sliding, overall stability of the structure, as well as the bending design of the foundation plate in the X and Y direction, separated into top and bottom. In addition, the following checks are shown. Punching shear checks both at the column control parameter and at the control parameter of the load introduced area, as well as various checks for the bucket foundation, for example, related to reinforcement. These are the design checks that are performed for this foundation in ULS. When I switch to the serviceability limit state, only the check for loads with large eccentricities remains in this example. This was a short overview of the result table. In the next step, I switch to the results navigator and show selected design checks graphically in the model. So let's take another look at the section at the top. In the results navigator, under design checks for the isolated footing, we can display the geotechnical design results. Within the ultimate limit state, you will find, among others, the design check with the number UL 7300, which represents the bearing capacity check. When we open this check, we can display the utilizations for each individual footing. In addition, the following information is shown. The applied actions and resistance represented as stresses, as well as the failure mechanism displayed graphically. This provides a very good impression of how the loads are transferred to the subsoil. Next, we have the sliding check. This check can also be displayed for each individual footing, and the corresponding utilization can be traced directly in the model. This is followed by the check for the structural stability. Since this check represents a tilting about a footing edge, it is also possible to display which edge is considered and in which direction the check is performed. This makes it very clear which edges are governing for the check and how the titling situation develops. The visualization can be reviewed for all relevant directions. Within the serviceability limit state, we also find the check for highly eccentric loading. This check can likewise be displayed graphically. In addition, the following information is shown: the existing eccentricity as well as the allowable maximum eccentricity, each given separately for the x and y direction. Under concrete design, you will find all concrete design checks that are performed as part of the footing design. First, we see the ultimate limit state. For the bending design of the footing slab, a total of 4 checks are carried out, each separate according to the direction and the position of the reinforcement. As an example, I will now show you the check UL 2100.02, which is the bending check for the bottom of the footing slab in Y direction. Within the bending check, we first see the design strips of the footing slab. For the design, the slab is divided into several virtual stripes, along which the required reinforcement is determined. In this example, these are design stripes 1 to 4, which cover different areas of the footing. In addition, within the bending check, the stresses in the soil footing interface can be displayed. These stresses are evaluated at the corner nodes at the footing, as well as below the center of the footing. In this way, both edge and corner stresses, as well as the average stress distribution beneath the foundation slab, are taken into account. Next, we take a look at the punching shear check. For this purpose, I select the check UL 2401, which represents the punching shear resistance at the column control parameter. In the results, we can see the ratios VED to VRD max, meaning the existing punching shear demand in relation to the maximum design resistance. This check verifies the local load-bearing capacity of the footing slab in the area of the column connection, where the load is introduced into the slab in a highly concentrated manner. Especially for isolated footings, this check is particularly important as it can be governing for the required slab thickness or the need for additional reinforcement. Below the slab and punching shear checks, the bucket foundation design checks are listed in the navigator. These are the checks UL 2106 to UL 2201. They mainly deal with the required reinforcement ratios in the socket, horizontal and vertical, as well as the bending checks of the socket wall due to the introduced column forces. Now in the navigator, we switch to reinforcement and then to isolated footings. Here, the reinforcement results can be displayed separately for each individual footing. Several visualization options are available. For example, required reinforcement shows the reinforcement that is required based on the design. The provided reinforcement represents the reinforcement that we previously defined. Not covered reinforcement directly shows if and where the provided reinforcement is insufficient. Required versus provided reinforcement is a very practical comparison view in which the required and provided reinforcement are overlaid directly. This overlay in particular is very suitable for a quick check whether the provided reinforcement is sufficient or whether adjustments are required in certain areas. Next, we take a look at the printout report. To do this, I first create a new printout report. In the printout report manager, I can precisely control which contents are included in the output. For the moment, I reduce everything to the essentials and deactivate all entries. First, I assign a name to the report at the top. I enter the name here and very creatively and simply call it printout report. Next, I selectively choose only the items that are relevant for the footing design. First, I activate the geotechnical analysis section, and here in particular the borehole profiles. This ensures that the soil layers used in the analysis as well as the groundwater level are documented in the report. Next, I switch to the concrete foundations design. For the isolated footing, I select the following items: geometry, reinforcement, bucket reinforcement, slab reinforcement, as well as the soil properties. In addition, I also include the global settings so that it remains clear later on which parameters and assumptions we used for the calculations. In the results section, I limit the selection to the tables that are relevant for the footing design. For example, the governing reactions, the governing internal forces, as well as the required and provided reinforcement, each evaluated per footing. This keeps the printout report well structured while still containing all essential information. Finally, I also activate the design overview. Here you can get a compact summary showing whether the design checks are fulfilled. In the next step, I generate the printout report and then go through the individual content directly in the report in more detail. I'm now directly inside the printout report and first switch to the cover page. Here I right-click on the cover page and enter the basic project information. This includes, for example, the client, created by, and the project name. As the client, I simply enter Dlubal Software, and for created by, I enter my own name, and as the project name, I choose Concrete Foundations Webinar. Next, I go through the remaining tabs. Under printer settings, you can define which printer is used, whether the complete report or only a specific page range is printed, as well as basic printing options such as copies or page orientation. In the Page Setup tab, you can define the paper format and the paper orientation. This is particularly relevant if the report is later used as a PDF or for printing. Under Option Settings, you can, among other things, configure headers and footers, adjust colors and table layouts, and control the page and sheet numbering. Here I also adjust the company information in the main text, that is the company name Dlubal Software and the address of the head office, Amtsellweg 2, 93464 Tiefenbach. These are purely formal details for the printout report, ensuring that it is clear and correctly labeled for documentation and distribution. Overall, this allows the printout report to be customized both visually and in terms of content to meet individual requirements. In the printout report, we first see the general project information we just entered. This information is purely formal. Below that, we see a model overview, which allows us to immediately recognize which structural model the printout report is based on. In the table of contents, we can clearly see which chapters are included in the report. The first technical section is the geotechnical analysis. Here, the selected boreholes are documented. You can see the individual soil layers with their thicknesses as well as the applied groundwater level. The only information missing at this point are the material properties of the soils. However, these can be added via Edit Printout Report under Materials. In the concrete foundation design section, we first see the isolated footings with their definition types and the assigned nodes. This makes it clearly traceable which footing is used at which position in the model. In the geometry section, the dimensions of the footing are listed. Here you can see, for example, footing length, width, and height, as well as the bucket geometry and information about the connected column. Next, the reinforcement results are shown. Since this is a bucket foundation, both the slab and the bucket reinforcement are listed separately. You can see the reinforcement types as well as the steel diameters and spacing. In the following section, you can see the soil properties. Here, the soil definition type is shown, in this case, multi-layered borehole, along with the subsoil conditions and the borehole used. This is followed by the global settings of the add-on. Among other things, the applied design approach is documented here, which is relevant for the bending capacity check, for example. In the results section, we first see the governing reactions. These tables show which loads and internal forces were governing for the individual footing. Next, the required and provided reinforcement is listed, evaluated separately for each footing. This makes it easy to understand where reinforcement is required and how it has been applied in the model. At the end of the printout report, you will find the design overview. Here you can get a compact summary of all performed design checks and their utilization ratios. This section is ideal for a quick plausibility check or as an overview for verifications and approval documents. The printout report, as we have seen it so far, already contains all relevant tabs and design results. To make the report more illustrative, additional graphics and detailed design check calculations can also be included directly in the printout report. I will start with the graphical representation. In general, the following applies. Everything that can be displayed in the graphics window can also be transferred directly into the printout report. First, I set up the desired view, for example, a utilization display. Afterwards, I can transfer this view directly via Add to Printout Report. In this way, utilizations, stress distributions, or design strips can be visually documented in the report. To keep the graphic clear in the printout report, I first adjust the model view. I start by hiding a few objects that are not required for this view. For the graphical representation, I now display only the foundation, the nodes, and the supports so that the focus is clearly on the foundation design check. Next, I go to the Result Navigator and select Design Checks, Geotechnical Design, Ultimate Limit State, and choose the sliding check, that is UL 7301, as an example. When I transfer the view to the printout report, the dialog Graphic Printout Send to Printout Report opens. Here I can define settings. For example, which information should appear in the image name, the image size and orientation, as well as image quality or color representation. Since the graphic appears a bit too dominant in the current size, I then adjust the image size directly in the printout report. Here I set the graphic to occupy 50% of the page height. The preview updates immediately, allowing me to directly see how the graphic will appear in the report. Alternatively, I could have adjusted the result limits beforehand in the control panel in order to maintain a better overview, especially for more complex models. In addition to graphics, individual design check details can be transferred to the printout report in the same way. To do this, I open the design check details of the selected check. In the lower right corner, the detailed calculation can then be transferred directly to the printout report. If we now switch back to the printout report, you can see both the previous added graphic and the design check details. Using drag and drop, these elements can be placed at any position within the report. In addition to the design checks and result graphics, the reinforcement layout can of course also be transferred graphically into the report. To do this, I switch to the concrete foundations in the model and then to the slab reinforcement. Using the corresponding option, I display the reinforcement layout. At this stage, I activate only the bottom reinforcement. The top slab reinforcement as well as the bucket reinforcement are intentionally deactivated in order to keep the visualization clear. This configured view can now be transferred directly to the printout report via the print option, just as we did previously with the result graphics. In this way, the reinforcement layouts can also be documented clearly in the printout report. With this, we have completed the printout report and have also fully finished this model. To conclude, I would like to show you one more option to defining the soil, namely using soil massive. Especially for more complex subsoil conditions or larger projects, this approach can be very helpful. For this purpose, I now switch to a different model in which several boreholes have been already defined. Using this example, we will take a look at how individual soil layers can be combined into a soil solid. I have now opened another model that already contains multiple boreholes. First, I delete the existing soil solid. Based on the boreholes, I now want to create a new soil massive. This opens the dialog Edit Soil Massive. First, I define how the soil solid should be represented. In this example, I work with the 3D finite element method and select boreholes as the definition type. This means that the soil of the solid is derived directly from the boreholes. In the upper right corner, I now assign the boreholes that should be used for the soil. In this model, these are boreholes 1 to 3. In the central area of the dialog, I then define the geometry of the soil solid. Here I specify the position of the soil solid in plane via the coordinates of the soil center. In this case, I select x as 7.5 meters and y as minus 7.5 meters. The dimension in x and y directions are, in this case, 30 meters. The height of the soil solid can either be defined manually or, as it is in this case, automatically from the boreholes. In addition, I can define whether groundwater should be taken into account. With this, the soil massive is fully described geometrically and can be used for the further calculation based on the boreholes. Next, I open one of the footings and change the definition type in the soil properties to multi-layered soil solid. In the lower right corner, I can then choose whether the graphic should be displayed area-wise for all footings or whether the graphic should be displayed node-wise, that is for individual footing nodes. Depending on the selection, both the graphic representation and the corresponding value table are updated immediately. Especially for models with a larger number of footings, this approach is very efficient. Only a small number of boreholes need to be defined. Each footing or each node is then automatically assigned to the appropriate soil properties, without the need to define individual boreholes for every single footing. With this, I've reached the end of my part. Together, we have looked at the design of concrete foundations, the geotechnical design checks, the creation and targeted extension of the printout report with graphics and design check details, as well as the multi-layered soil definition using boreholes and soil massives. I hope this has given you a good overview over the workflow and the possibilities within the Concrete Foundations add-on. Thank you very much for your attention, and with that, I would now like to hand back to Andreas.
Thank you, Ann-Kathrin, for your presentation. At the end, I have an additional hint to our online courses. There's the RFEM 6 course. It's a course for beginners. Then the Eurocode 2 course for the reinforced concrete design, the Eurocode 3 course for the steel design, then the Eurocode 5 course for the timber design, the Eurocode 8 course for the earthquake design. And you can find more information when you scan the QR codes or click at the links here. You can get such a course for free when you submit your customer project, and when we publish that project. To submit your project, just scan the QR code or click at the links. You can also write an email to me to info@dlubal.com, and I will write you what data I need. It is not much work for you. Then our free online services, for example, the Dlubal community, you can ask questions there, for example, about our software. Then our colleagues will answer you, or our community members, our users of our software. Then there's the Geozone tool. You can determine snow, wind, and earthquake loads there on that page. Then the cross-section property page. Then you can download 3D models, for example, as template for your project. If you don't already use our software, you can download the 90-day trial versions of RFEM, RSTARP, RWind, and RSection. Then, you can explore all our free services when you click at that link, or you can scan the QR code. You can find more information, such as recorded webinars, the knowledge base article on our website, dlubal.com. You can also ask our AI assistant Mia all the time, 24/7. Just try it. Okay, that should be also all from my side. I thank you for your attention. Thank you, Ann-Kathrin, for the presentation. I wish you all a nice rest of the day. I hope we meet each other in a future webinar. See you. Bye-bye.